Okay, so now we discuss on adiabatic mixing of air streams. So basically, mixing is when you have two ducts combined together become one duct section, right? So you have a ducting number 1 plus ducting number 2 mixing together become the output become ducting number 3. So what we're gonna analyze is actually the mixing section. Okay, so first we need to do some balance of mass of dry air and mass of water vapor, and also the energy balance. Okay, so for the mass of dry air, so you're gonna have mass flow rate of dry air at ducting number 1 plus m dot A2 is going to equals to m dot A3. Next is the mass balance of water vapor. So you're gonna have m dot A1 omega 1 plus m dot A2 omega 2 equals to m dot A3 omega 3. Next is energy balance. Similarly, you have m dot A1 H1 plus m dot A2 H2 equals to m dot A3 H3. Okay, from this energy balance, later what we're gonna do is we want to produce one equation which can represent the mixing section, and then from that equation we can determine all the mixing value if other value is known. Okay, so let's say from mass of water vapor, okay, you have m dot A1 omega 1 equals plus m dot A2 omega 2 is actually equals to, now we're going to substitute the mass of dry air, okay, which is m dot A1 plus m dot A2 equals to m dot A3. So this equation become multiply with omega 3. Okay, so we're going to expand this one. Okay, next we're going to rearrange something like this. So this one become m dot A2 omega 2 minus m dot A2 omega 3 equals to A1 omega 3 minus m dot A1 omega 1. Okay, so we're gonna simplify this one, becomes m dot A2 omega 2 minus omega 3 equals to m dot a1 omega 3 minus omega. Okay, we're gonna rearrange this one into some sort like a ratio. So it becomes, let's put it something like this, m dot a1 divided by m dot a2. So this one is going to equals to m dot a1 divided by m dot a2. So meaning this one is omega 2 minus omega 3 divided by omega 3 minus omega 1. Yes. Okay, so this portion. Alright. Okay, so similar approach we're gonna do for energy balance. So later what you're gonna have is the enthalpy arrangement. H2 minus H3 divided by H3 minus H1. Okay, so this is the equation that we're going to use to analyze or important for mixing section, okay, or mixing chamber. Okay, let's do one example. Okay, so but before that, let's take a look at the psychometric chart here. Okay, so when you mixing up two ducting, you have state number 1 and state number 2. So those mixing outcomes will be in between, which is state number 3, right? So that's how it looks like in the psychometric chart. So let's do some example. So let's read the example. Saturated air leaving the cooling section of an air conditioning system at 14 degrees C at a rate of 50 meter cube per minute. So it's mixed adiabatically with the outside air at 32 degrees C and 60% relative humidity at a rate of 20 meter cube per minute. Assume that the mixing process occurs at 1 atm. So meaning you can use psychometric chart. You need to determine all these 4 values. Okay. Okay, so let's draw the mixing section. We have a ducting, something like this. So temperature 1, 14 degrees C, and then V.1 equals to 50 meter cube per minute. So saturated air meaning relative humidity is actually 100%. Next you have temperature 2, which is 32 degrees C, and then relative humidity 60%, and then V.2 equals to 20 meter cube per minute. So the pressure occurs, the operating pressure is 1 atm, right? So you need to determine B.3 omega 3 relative humidity 3, and then temperature Q. Okay, alright. Okay, so since the problem is in 1 atm pressure, so we can use psychometric chart to analyze, to solve the problem. Okay, at step number 1, temperature 1 is 14 degrees C and relative humidity is 100%. So meaning 14 degree, 14 degree, this is 14, 100% relative humidity. Okay, so this is state number 1. So next we draw for state number 2, 32, right? 32 degrees C. And then 60% relative humidity, this is 60%. This line is 60%. This line 60%. So meaning this is state number 2. Okay. So what you do is you draw a straight line in between these two states. Okay. So state number 3 is going to occur in between these two states. Okay, from 1 and 2. So state number 3 is going to occur in between these two states. Okay, so before that, let's determine the enthalpy, the omega, and the specific volume for each states, state 1 and state 2. So for enthalpy, okay, for enthalpy for state 1 is 39.4 kilojoule per kilogram. And then omega this one, so 0.001230 grams, and so 0.010 kg H2O kg A. Right, this straight line from here to here. Okay, next is V1, specific volume. Okay, so this is 0.82, this is 0.84, so meaning this is 0.83. So here perhaps the value is 0.825826. Okay. So V1 0.826 meter cube per kilogram. So similar approach we're gonna do for enthalpy. Okay, mind my drawing. Yours must be, you need to use ruler, right? Alright, enthalpy here is 79.0 kilojoule per kilogram. Right. Omega 0.0182 kg H2O per kilogram dry air. And then V1, so around 0.889, right? Sorry, V1, V2, 0.889 meter cube per kilogram dry air. Okay, so now we have all three values, and then we can use this value to find what we want from the problem. All right. Okay, so let's calculate m dot a1. M dot a1 equals to v dot 1 divided by specific volume 1. So from there, you're gonna get 16.5 kilogram per minute. Okay. Since v dot 1 is given 50 meter cube per minute, right? So similarly, we can calculate for m dot a2, v dot 2 divided by specific volume 2 from 20 meter cube per minute and 0.889 for specific volume, you're gonna get 22.5 kilogram per minute, right? Now we already have mass flow rate A1 and mass flow rate A2, so from there we can have m dot A3, which is equals to m dot A1 plus m dot A2, the mass balance of dry air. So the value would be 83 kilogram per minute. Okay, now we use the equation, or I can call it as a mixing equation. Okay, m dot a1 divided by m dot a2 equals to omega 2 minus omega 3 divided by omega 3 minus omega 1 equals to h2 minus h3 divided by h3 minus h1, right? So we have this value, omega 1 and omega 2. We also have this one from the psychometric chart. H2 and H1, we also have determined that. So meaning from there, we can have omega 3. Okay, so omega 3 is gonna equals to 0.0122 kg H2O per kilogram dry air. And we can also find H3. H3 is 50.1 kilojoule per kilogram dry air. Okay, now since we already have two informations, okay, so meaning we can use psychometric chart to find state 3. Okay, remember during previous class or section, I explained that not only dry bulb temperature and relative humidity can be used for cytometric chart. Any two values that we have, so we can use that to determine the state, right? So let's take a look at psychometric chart. Okay, H3 is 50.1, so we take a look at the enthalpy. Okay. So this is 51, so 50.1 more or less similar to 50. So this line, okay, we draw at that position. And then the line of omega, we draw until it crosses this line. Okay, alright. So suppose this red color should be on top this blue line, but this is due to my drawing, right? Okay, this is due to my drawing. So what we have is, let's determine the temperature. So this is T dry bulb at step 3. Okay, and then if you want to determine the relative humidity, also you can find from here. Okay, so yeah, if any two value that we have, so we can cross it together and find all the properties on that position. Okay, so the value that we want is at state number 3, dry bulb temperature, which is T3, 19 degrees C, and then relative humidity, we're gonna get 89%, and then specific volume 0.844 meter cube per kilogram. Right. So meaning we already found omega 3, relative humidity 3, and then T3. Next, you want to find V dot 3. Okay. So from V dot 3, we're gonna use M dot A3, V dot 3 divided by specific volume 3. So basically, V dot 3 is actually M dot A3 multiplied by specific volume 3. Okay, so we already have these two values. Okay, sorry, M dot A3, this one. Okay, and then specific volume 3, this one. So V dot 3 is 70.1 meter cube per minute. Alright, done. Okay, so for next class, we're going to proceed with cooling tower.